Hello everyone, welcome to the lecture 25 in this course on diffusion in solids. So, today's is a tutorial lecture where we will try to solve some problems on the concepts that we have covered in this week, namely the free energy versus composition diagrams. So, we said some basic thermodynamic concepts we revisited, then the basics of interdiffusion, how the phases form in the interdiffusion zone, how we draw the composition profiles for different kinds of phase diagrams and so on. So, let us look at some of the problems which will also help you in solving the assignments later. So, the question number 1 is a objective type question which says which of the following statements are true regarding interdiffusion coefficient for a binary diffusion couple of two pure metals. A, it is independent of concentration, B, it is a function of annealing temperature, there is only one interdiffusion coefficient for a given binary diffusion couple, or each constituent will have a separate interdiffusion coefficient. So, just take a moment before you proceed with the video so that you can see whether you understood the problem correctly or not. Remember that in the questions in the tutorial we have seen, you can have multiple correct answers in the objective. Same thing will follow in the assignments also. You may have certain questions where more than one options are correct. So, now if we talk about this question, binary diffusion couple, which is so d tilde. So, you know for a diffusion couple, this is a typical profile that develops in the interdiffusion zone. And the thing is that if you remember the equation that we write, dou C by dou T is equal to dou by dou X of d tilde dou C by dou X. And because here the composition is changing of A and B, we can no longer assume that D is independent of concentration. So, therefore, option A is not correct, because it says it is independent of concentration, whereas the T tilde or this interdiffusion coefficient is actually dependent on the concentration. Then it is a function of annealing temperature. Yes, like any diffusion coefficient, the interdiffusion coefficient also is exponentially related to temperature. So, the D is equal to D naught exponential minus Q by RT. Arrhenius kind of relation is usually found to be true here. Now, the third is there is only one interdiffusion coefficient for a given binary diffusion couple. This we will also elaborate later in one of our lectures, but what we have seen in this week, yes, there is only one interdiffusion coefficient. So, the fact that we write or we call it as interdiffusion, and the rate at which this intermixing happens is what is measured by this interdiffusion coefficient. So, there is only one interdiffusion coefficient for the AB system. We do not write d tilde A or d tilde B, we just write d tilde or d tilde AB if we want to indicate the system. So, therefore, naturally the fourth option is not correct. Each constituent will have a separate interdiffusion coefficient. This is not true. There will be only one for a given binary diffusion couple. So, therefore, the correct answers are B and C. Now, the second question, for certain conditions, two elements A and B show two phases P1 and P2 at equilibrium. Which of the following statements is then correct, where mu is the chemical potential? So, this you must recollect from discussion in our lecture on the thermodynamic concepts, where I showed you this graph. So, for example, if you have free energy of alpha and free energy of beta, here the solid lines, green color represents G alpha, blue color represents G beta. And what is chemical potential? Chemical potential is how do you get from this graph? Is you draw a tangent at this point, wherever it intersects A axis, it gives mu A in that particular phase. Now, when you have two phases in equilibrium, in this case P1 and P2, then what happens is that the tangent, the common tangent, that means this red line is a tangent to G alpha also and tangent to G beta also. What it means is, wherever this tangent intersects the A axis will not only give me mu A in alpha, but it will also give me mu A in beta. Similarly, wherever it intersects the B axis, it will not only give me mu B in alpha, but mu B in beta as well. Therefore, what it means is that when the two phases are in equilibrium, that then the mu A of mu A in alpha has to be equal to mu A in beta. Similarly, mu B in alpha has to be mu B in beta. In this case, alpha and beta we are denoting as P1 and P2. So, we write mu A in P1 should be equal to mu A in P2, and mu B in P1 should be equal to mu B in P2. So, the correct options are A and B. Moving on to the next question. Two elements A and B show isomorphous phase diagram with miscibility gap at lower temperatures. Which of the following statements are likely to be true? So, we have seen this example, two elements A and B with isomorphous phase diagram and miscibility gap at lower temperatures. So, we know that the delta H mix is equal to omega XA XB. So, the miscibility gap arises. So, that means they like to separate out, they like to repel each other, which means that omega is positive. Okay. So, the omega being positive means that A and B like to repel each other, so which is what creates a miscibility gap. So, the first option is correct, that the interaction parameter omega is positive at lower temperatures. Now, usually this is again we have seen in our slides that when A and B form isomorphous phase diagram is when they have a similar crystal structures. Remember, they only have a miscibility gap at lower temperatures. At higher temperatures, which is above the miscibility gap, they exist as a single phase solid solution, which usually happens when you have a similar crystal structure. So, the correct options here are A and C. Remember, this is just to show you again that when they have a miscibility gap, that means the omega is positive at lower temperatures, the free energy curve looks like this. The delta G mix is positive for certain composition range, and therefore, you get the miscibility gap. Now, moving ahead, two students of this course carried out series of binary diffusion couple experiments at various temperatures between 300 to 800 degrees centigrade, with the N members being A 0.25, B 0.75, A 0.75, B 0.25. However, they did not observe any interdiffusion zone in SEM. Select the possible reasons. That means, they made a diffusion couple with these two alloys, and they did annealing at various temperatures, but they did not observe any interdiffusion zone in SEM. What may be the possible reasons? So, the first case is the first option is the kinetics of phase growth are extremely sluggish in the temperature interval of experiments. That is why they did not see interdiffusion zone. This is very much possible. We have seen, for example, in several cases only certain phases form at certain temperatures. So, it is not necessary that when you do a diffusion couple, whatever the phases are present in phase diagram must form. It depends upon the kinetics. So, there is a possibility that the kinetics of phase growth are so sluggish that you do not see any interdiffusion zone. Second is composition of N members lie in two phase field. So, this I think we have seen that when we have a phase diagram which is, let us say, of this kind, where there are two phase regions, there is a single phase region, again two phase region, and we had seen that if you plot a chemical potential diagram as a function of composition, in the two phase regions the chemical potential remains same. The mu B remains horizontal in both these regions, which means that if you make a diffusion couple of these alloy P and Q, there will be no gradient in chemical potential, and if there is no gradient in chemical potential, there will be no diffusion taking place. Remember, we derived this, we understood this from G versus X curve, that it is the chemical potential gradient which really drives the diffusion. In most of the cases, it is same as concentration gradient, but it need not be true. For example, here you may see that okay, Q has a higher amount of B than P, but the chemical potential is same, and therefore you don't see a phase growth. So, yes, it is possible that these two alloys may lie in the two phase region, and therefore there is no phase growth. Remember, this phase diagram is not for these systems. It is just an exemplification to show that if these two lies in the same phase field, in a two phase region, then it is possible that interdiffusion does not happen. The third option is also interesting. The phase growth is not observable in SEM. It is true actually, because SEM has limited resolution, although it is higher than optical, but SEM also has its own limitation of how much resolution it can be. So, there are some times, in fact, when people do detailed interdiffusion analysis, at the interface people prepare the sample using focused ion beam technique, so that they can put it in transmission electron microscopy. There only they are able to see very thin phases that develop, which may not be observable in SEM. So, in this case, all the options A, B and C are correct. So, this is the graph I showed for P and Q. The chemical potential will be same, mu B and mu A both are same, and therefore, it is possible that if the composition of two end members they lie in the two phase field, the interdiffusion zone may not develop. Question number 5, a phase mixture can grow in interdiffusion zone of a dash diffusion couple. So, this we try to discuss in terms of Gibbs phase rule. So, for example, we know that the condensed Gibbs phase rule, because usually in interdiffusion experiments the pressure is constant like in many of the metallurgical process. So, F, the degree of freedom, is equal to C minus P plus 1, or P, which is the number of phases that can develop, is equal to C minus F plus 1. So, in the interdiffusion zone, we know that usually the interdiffusion zone annealings are conducted at a constant temperature. So, these are isothermal experiments. So, therefore, this 1 will also go. Remember, in the Gibbs phase rule, the original phase rule F equal to C minus P plus 2, these two variables are pressure and temperature. In the condensed phase rule, pressure is constant, so we have plus 1. Now, because temperature is also constant, so we will have simply P equal to C minus F. Now, in the interdiffusion zone, a typical interdiffusion zone looks like this. So, you can clearly see here that composition is already varying. So, therefore, 1 degree of freedom is already utilized, which means that minimum value of F in the interdiffusion zone is already 1, okay, because here the composition is varying. So, the minimum value of F is 1. Therefore, the maximum value of P can be equal to C minus 1. Okay. So, therefore, if you put C equal to 2, then you get P max as 1. So, that means for a binary diffusion couple only single phase regions can grow, and this we have also seen with several practical examples that actually in the binary diffusion couple only single phase region grow. So, therefore, now in this question a phase mixture can grow in the interdiffusion zone of a. So, it can go C equal to 3, C equal to 4, C equal to 5. So, either you can write as a non-binary diffusion couple, or if you write either ternary, quaternary, quinary, those are also acceptable. Okay, ternary or higher component diffusion couple. So, now moving to question number 6. A diffusion couple is formed from two metal blocks containing XA moles of A and XB moles of B respectively. After annealing for a very long time, a single phase exists throughout which has a free energy of 3 joule per mole. If the free energy of assembly before the start was 8 joule per mole and the entropy of mixing is 5 millijoule per mole Kelvin, calculate the temperature at which the diffusion annealing was performed. So, assume the ideal solid solution behavior. Now, let us see how do we approach this. So, the total free energy after the diffusion annealing is written as G2 is equal to G1 plus delta G mix. That means, after the solid solution has formed completely, this is the total free energy, which is the G1, which is the initial free energy plus delta G mix. Now, what is given to us? That before the start of the assembly, it is 8 joule per mole, and G2 is equal to 3 joule per mole. That is the free energy of the solution. Therefore, the delta G mix, if you put simply in this equation, is equal to minus 5 joule per mole. Now, we know that delta G mix can be written as delta H mix minus T delta S mix. But since we have to assume the ideal solid solution behavior, we know that for the ideal solid solution, the delta H mix is equal to 0. Therefore, the delta G mix can be written as minus T delta S mix. Now, given that delta S mix is equal to 5 millijoule per mole Kelvin. So, remember it is millijoule, so we should convert it into joules. So, this will be 0.005 joule per mole Kelvin. And then you can calculate the temperature by taking the ratio of delta G mix by delta S mix, and the temperature comes out to be 1000 Kelvin. Let's go to next question. So, the next question is refer to the ALGD phase diagram below, that is the aluminum gadolinium phase diagram. The first part says draw the variation of chemical potential of gadolinium as a function of its composition at T equal to 600. Second, a diffusion couple is formed between pure gadolinium and pure aluminum and annealed at 600 degrees centigrade. So, this red line for 100 hours. And the microstructure analysis revealed that only phases ALGD2, ALGD and AL3GD grow in the interdiffusion zone in the thickness ratio of 3:2:1. Now, based on this information, sketch the corresponding composition profile after the interdiffusion annealing. Remember, we have seen in our lectures that it is not necessary that all the intermetallic phases will grow in the interdiffusion zone. So, therefore, as given in the question, when you draw the composition profile, only these phases have to be drawn. However, when you draw the chemical potential of GD as a function of composition, all the regions have to be included. So, the first part, the chemical potential, we saw that for the solid solution phase, there is a small gradient in the chemical potential. So, here as we have seen, the solid solution region is very small. So, therefore, you see this is actually still exaggerated. Then you enter a two-phase region. So, you can even count that how many two-phase regions are there, and that many horizontal lines will be coming. And because these intermetallics subsequently grow in the gadolinium content, so their chemical potential of gadolinium will keep on increasing. So, you see here, then here, then this value is higher, this value is higher, then this is the last region with gadolinium solid solution, and finally the pure gadolinium. So, this is how you can draw the chemical potential graph. So, you can see, count here the number of two-phase regions, and the same is reflected in the phase diagram as well. And the second part, as I said, that not all these regions need to be visible in the interdiffusion zone. In the question, it was given that you have ALGD2, ALGD and AL3GD in the ratio of 3:2:1. So, you remember when you draw the composition profile, that ratio approximately has to be maintained. So, the ALGD2 is the thickness is the maximum, followed by ALGD, followed by AL3GD. Another thing that you remember from an assignment point of view or from an exam point of view, you see the composition of the intermetallics. GD2 has the maximum gadolinium content. So, this has to be near to the GD, followed by AlGD, followed by Al3GD, and then finally gadolinium composition in pure aluminum has to be indicated as 0. So, this is how you can draw the composition profile. So, these are the correct answers for the first and the second part of the question. Now, question number 8, draw the variation of Gibbs free energy of mixing for a regular solid solution of A and B having positive value of interaction parameter at high and low temperature. What will be the values of dou delta G by dou XB as XB tends to 0? Will your answer change if the solution exhibited ideal solid solution behavior? So, the first part, that is the Gibbs free energy of mixing for a regular solution where omega is positive, the interaction parameter is something like this at higher temperatures. We saw that delta H mix is equal to omega XA XP. So, if omega is positive, then delta H mix is positive throughout. And T delta S mix is a negative term, because delta S mix is always a positive quantity. So, minus T delta S mix will always be in the negative quadrant, and therefore, this will lie here. But because the temperature is high enough, therefore, the combination of these two, the delta G mix, will still be negative in the entire quadrant. However, when you are at a lower temperature, we have discussed this, that at lower temperatures the minus T delta S mix is not enough to overcome the delta G mix at all the compositions. So, therefore, for certain composition range, in this case from here to here, you have the delta G mix being positive. So, at lower temperatures when omega is positive, you can have a situation where the delta G mix is positive for a single phase. So, therefore, this system then in this composition range at this temperature will not exist as a single phase, but rather exist as two-phase mixture. Now, for the second part of the question, what will be the values of dou delta G by dou XB as XB tends to 0? So, the delta G mix for the regular solid solution is written as omega XA XB plus RT XA ln XA plus XB ln XB. Now, this if you differentiate with respect to XB, then you get omega into 1 minus 2 XB. How do you get that? Remember, you can write XA as 1 minus XB, and then you apply the product rule of differentiation and you will end up in this term. So, this is omega into 1 minus 2 XB plus RT. Again, XA also you can write as 1 minus XB, and then by simple application of the product rule and certain cancelling of the terms, you will get RT ln XB by XA. So, this in between steps I leave it to you, it is pretty straightforward. So, you can write RT ln XB by XA. Now, as XB tends to 0, this term when XB is 0, this term is 0, therefore, this in the bracket you tend to get to 1. As XB tends to 0, XA tends to 1, so this denominator also becomes 1. However, when you have XB tending to 0, there you are talking about log 0. And log 0, if you remember the graph of logarithmic function, we have also seen that in our lecture on the revision of mathematical concept, that log 0 is actually minus infinity. So, therefore, as XB tends to 0, this quantity tends to minus infinity. So, this there is a small correction I will just do as a typing mistake here. So, this should be actually R. So, dou delta G mix R by dou XB tends to minus infinity as XB tends to 0. Now, if it is an ideal solid solution, you have this term omega is 0 and you have only the term RT XA ln XA plus XB ln XB. And therefore, you can see that the differentiation of this with respect to XB will give you RT ln XB by XA. this again will go to minus infinity as xb tends to 0. So, as xb tends to 0, dou delta G mix ideal by dou xb will also tend to minus infinity. So, this answer does not change irrespective of the solid solution behavior. Actually, what does minus infinity mean? Minus infinity means that a small addition of xb tends to 0 means that it is slightly more than xb. So, small addition to of xb will cause a very large change in the free energy of the solid solution, will lead to a very large value of delta G mix, which tells us that a small addition of xb is always favored, and therefore, it is not usually possible to obtain 100% of A, because a small addition of B will always lead to a large change in the free energy of mixing. Okay. So, we will continue in the next week. So, with this we will end today's lecture and continue with next week. Thank you.